We look up at the night sky and see clockwork. The planets trace their predictable circular loops around the sun, keeping us at exactly the right distance to stay warm and alive. From down here, it feels like a serene, highly ordered system. But that stability is a recent luxury. Space is entirely unforgiving. For most of its history, our solar neighborhood has been a chaotic firing squad of rogue rocks, overlapping gravitational poles, and lethal radiation. 66 million years ago, a 6-mile-wide rock slammed into the Gulf of Mexico, moving at 8 miles a second. The impact released the energy of 5 billion atomic bombs, triggering global wildfires and a suffocating winter that completely wiped out the dinosaurs. We can still touch the physical fallout from that exact moment. In this rock formation, the light-colored stripe resting right above the quarter is the KT boundary. Below it, dinosaur fossils are everywhere. Above it, they completely vanish. That specific layer is packed with iridium, an element incredibly rare on Earth's surface, but common in space rocks. It is easy to look at that dead zone in the rock and see only destruction. But consider the alternative. Imagine a version of our solar system where the planets formed in total peace. No massive collisions, no exploding stars, no incoming orbital debris. Without that continuous chain of extreme violence, we wouldn't have a habitable world. The exact same forces that threaten to wipe out life today are the precise tools the universe used to engineer our planet in the first place. 4.5 billion years ago, our solar system did not exist. There was only a stellar nursery, a massive, freezing cloud of sparse gas and microscopic dust particles floating silently in a vacuum. Left alone, it would have stayed that way forever. To compress that tenuous mist into dense stars and planets, you need an immense amount of pressure. That pressure arrived with the death of a giant star. A supernova exploded, sending a wall of superheated plasma racing across space at 70 million miles an hour. It smashed into the dust cloud and crushed it inward. Inside that newly crushed cloud, gravity was still too weak to pull the microscopic grains together. Instead, as the particles bumped into each other, they built up a tiny static charge. Through this electrostatic force, they began to cling to one another, much like clothes sticking together in a dryer, forming fluffy, fragile clumps. If that neighboring star had never detonated, those floating grains of smoke-sized dust would never have been forced close enough to stick. The very first physical building blocks of Earth required a stellar execution. As those dust clumps grew into rocks, and rocks into asteroids, the early solar system turned into a chaotic construction site. Thousands of misshapen protoplanets hurled around the sun at 20,000 miles an hour, shattering each other in a relentless 30-million-year demolition derby. The Earth survived the gauntlet and grew, but it couldn't dodge the largest incoming threat. A Mars-sized planet named Theia hurtled toward us. By sheer chance, it didn't hit dead center. It slammed into the Earth at a glancing angle, ripping the world open and blasting a colossal ring of molten rock into space. The impact completely liquefied the young Earth. The heavy iron from Theia separated from the lighter surface rock and sank into the planet's core. That swirling mass of molten metal generated an intense magnetic field around the globe, an invisible shield that still protects our atmosphere from being stripped away by solar radiation. Meanwhile, the millions of tons of debris blasted into orbit eventually clumped together to form our moon. Because the moon is unusually massive compared to the Earth, its heavy gravitational pull anchors our planet's tilt, giving us the steady, predictable seasons required for complex life to evolve. A direct hit would have blown the Earth to pieces. Instead, that apocalyptic collision delivered the radiation shielding and the climate stability that keeps us alive right now. Despite surviving Theia, the young Earth was still a barren wasteland. Any water in the inner solar system had long been vaporized by the intense heat of the early sun. To get oceans, we needed an outside delivery. Hundreds of millions of miles away, the solar system's gas giants hadn't yet settled into stable orbits. Jupiter and Saturn fell into an intricate dance, and their combined gravity began pulling wildly on everything around them, heavily destabilizing the outer solar system. This gravitational turmoil acted like a cosmic bowling ball hitting the outer asteroid and comet fields. Billions of ancient icy rocks were scattered inward, For hundreds of millions of years, they rain down on the dry Earth. Comets and outer asteroids are essentially dirty snowballs. With every impact, they deposited frozen ice that quickly melted in the heat of the young planet. Over millions of years, this brutal bombardment literally filled our oceans. The space rocks we monitor today as potential civilization enders are the exact vehicles that delivered our water. Without a massive, system-wide orbital destabilization, the Earth would have remained a permanently parched desert. Today, we can walk outside, feel the warmth of the sun, and look at a planet covered in lush green forests and deep blue oceans. It feels remarkably safe. Yet to get here, we had to thread a needle through billions of years of catastrophes. We needed a star to explode at exactly the right distance to compress our dust. We needed a Mars-sized planet to hit us at precisely the right angle. We needed gas giants to go rogue and hurl ice at our surface. The universe is deeply hostile, and one day another rock will inevitably cross our path. But when we look up at the night sky, we shouldn't only see threats. The supernovas, the asteroids, and the wandering planets carry immense destructive power, but they are also the only forces capable of building a world.